Hey, welcome to this tutorial. This is going to be a follow-up tutorial to the most recent one. The problem statement for that tutorial is what you're looking at here on this slide. We had a solid block of material. The top wall is at 500K, the sides and the bottom were at 300K, and we were interested in finding the steady state distribution. A material property that we input into the OpenFOAM files was my thermal diffusivity, in this case 1e to the minus 4. And if you recall in that tutorial, the files were basically just all given to you, and you were taught what to type in the OpenFOAM commands, and you got the results, and you were able to follow along, hopefully, with that tutorial. And for this tutorial, I wanted to give some insight into how I created those files, where I got them from, and hopefully by illustrating that process you learn a little bit more about the file structure of OpenFOAM, where things are located, what different lines mean, and the importance of being consistent between the different files. And so to start this off, we can go to our tutorials here by typing foam tutorials. And if you recall, this was in the basic folder, and it was a Laplacian foam. The title of this one was flange. And so I'm going to copy this entire thing. Actually, let me show you something real quick. I can be anywhere, and I can type change directory home, and I go back to my root folder. This is not located on my C drive or D drive, and so I want to copy all these OpenFOAM files to a local drive so that I can tweak them and run them. I don't want to mess with anything in the tutorials folder. And so in this home directory, I have a shortcut called my foam folder, and that is pointing to a location on my local drive, on my D drive. So right now, in that location, which is just a folder called OpenFOAM, I don't have any files or folders. But if I go back to my foam tutorials, go back to basic and Laplacian foam, I'm going to copy that entire directory and all the subdirectories and files to that home and then my foam folder. And you can see that now I've got this flange folder on my local drive where I can do all sorts of things with it. And we talked a little bit last time about this all run script. We can take another look at it really quick. It had a series of commands that it was going to run in the background, and the first was to create the mesh given the ANSYS file. That's what this one is here. That's my ANSYS file of the solid model, and I'm going to create a mesh as part of that all run script. That mesh is not here right now. If I go into constant, it's just got the transport properties. Recall that when we create the mesh, there should be another folder in here called polymesh with a series of files that are located within that folder. And so I haven't run anything. I don't have anything. I don't want to use the ANSYS model. I don't want to use any of these scripts here, so I'm just going to delete those. I want to create a very simple mesh because this is a very simple problem. I'll use the block mesh utility within OpenFOAM. The problem is I don't have anything in here in this tutorial set of files for a block mesh because it wasn't designed to do that. So what we will do is simply go to our foam tutorials, and we will talk about in the next series of tutorials we'll look at convection diffusion problems, where again right now we're just doing diffusion only, but convection where we have a flow field that we're interested in determining. So if I come into the incompressible, I've got a whole series of solvers there. We will talk about these, not all of them, but a few of them. The first one I'm going to just look at is in this icofoam folder. There's two different types of simulations in there. So I'm going to go into the cavity folder, and then there's different versions of the cavity. I just want to take that cavity. I don't want cavity clipped or cavity grade. And this is, if you go to the user guide for OpenFoam, then this is the first one that you start out with. You start out with this cavity, which is a square, and this is why I'm copying these over, is because I just want that block mesh. And I'm going to take that square and adapt it to my problem. But what this is a cavity where the side walls and the bottom wall are fixed surfaces, and the top wall is one that's moving at some velocity. And so I'm going to get some flow, circulation, behavior inside that cavity that I want to characterize for this particular tutorial. But again, I don't really want any of that. In fact, I don't need to copy the whole directory over. I'll go ahead and do that, but I really only want the block mesh file. But we'll copy the whole thing over and talk about some of the files in there. Okay, so now I come here and I've got a cavity folder and I've got a flange folder. And so within this cavity, I've got the same file structure. I've got a 0. Instead of temperature, I'm looking at pressure and velocity. But the file structure is the same. I'm going to define the units. I'm going to specify some internal fields. So for this one, there's 3 components of velocity. So I'm specifying initially everything's at a standstill. I've got 0 velocity everywhere. And then I apply my boundary conditions to each of the boundaries. So the boundaries in this case are defined as moving wall, fixed walls, and front and back. And so I want to be very careful that I keep the same exact names in all my files. So in my pressure, if I look at that, then you'll see that it is named with boundaries exactly the same as my U. And it shouldn't be surprising that if I go into my block mesh file in the system folder, my block mesh dictionary, then this is what you were just given in the previous tutorial. And everything that we have here is essentially the same for our problem. We're going to create 7 points, and then we're going to create blocks based on those points. We're going to define a mesh. In this case, we've got 20 elements by 20 elements by 1 element in the Z direction. And I'm going to have a simple grading, meaning I don't have any expansion ratio in either of the 3 directions. They'll be uniform in each of the respective directions. And then I go define my boundaries. And notice here, again, I've got moving wall, fixed walls, and front and back. And it's important to note, and you might already realize this, presumably, but I don't have anything. The mesh doesn't care. It's agnostic to what solver I happen to be planning to use. The mesh is just there to create a mesh and nothing else. And so I don't need to worry about the fact that this was in an icofoam, which is a convection diffusion set of problems, and I want to use it in my diffusion only example. So I don't need to worry about that. I just need to worry about naming of the boundaries and keep those consistent across all my files. So I can come in here and let's change directories from the tutorials back to my home. And I can come in here to my, I don't know why I didn't, there we go. I can come in here to the cavity, or the flange, that's what I'm working with, the flange. And I've already copied over that block mesh dictionary, so it should be here in my system folder, and oh, I didn't copy it, I thought I did. So we want to copy this from my cavity to the flange folder in the system. And before in the cavity, you notice I had these 4 files, and I've got a control dictionary and FB schemes and FB solutions. I didn't have a block mesh dictionary, again because this tutorial, the flange, was finding its mesh based on the ANSYS file, and so I didn't need a block mesh dictionary file. I wasn't creating the mesh in that fashion, but I am now, and so I want to make sure I have that in there. So if I come to we got my block mesh dictionary in there now, and just to prove that this is completely agnostic, I'm just going to run my block mesh utility. I need to change directory to the flange directory, not in the system, and then run my block mesh. And you notice I don't have any errors, and the patches, the names of my boundaries, are moving wall, fixed walls, and front and back, because that's exactly what I had defined in my block mesh dictionary file. So let's take a look at that. We got moving wall, fixed walls, and front and back. And so really all I need to do is, well, I just created the mesh, right? So if I come to my root directory, I'll create a file here, and I can go open this up in pair view. And I've got a square domain. I can take a look at the edges to make sure that my mesh has 20 by 20. That's what I thought I was doing. I want to make sure that it looks like I am expecting. And notice here I don't have any other options. I don't have a temperature or anything else for that matter, because I haven't run the solver. But I can go look at my mesh, and I can take a look at some of these down here, these mesh regions. So right now it's the only one highlighted is the internal mesh. If I take this off, then I've highlighted nothing, so nothing's going to show up. But I can take a look at these fixed walls, and I can look at my boundaries, and I can make sure, again, before I run the solver, that everything is what I think it is. I thought I defined the fixed walls as these 3, so I just want to verify that. And then I can look at the moving wall, which should just be that top wall, and then I can look at front and back, which is obviously the front and back. So what we want to do, though, is we want to come in here and rename some of these. So I'll come to my block mesh dictionary, and I don't really have a moving wall, so I'm just going to call this my top wall. And my fixed walls are going to be, I think we named those side bottom walls. And I'm going to leave the front and back as the front and back. And this now, if I save this and I run my block mesh utility again, I've created a mesh and it wrote over the previous one. And now I've got something, my 3 patches are called top wall, side bottom walls, and front and back. So coming up back to pair view, I can refresh this or reload this, and I'll get some additional boundaries here that are consistent with how I just redefined them, but it's better just to reload it here like this, and so just delete this one. And you'll see that I've got in my boundary descriptions, I've got my new labels. I've got front and back still, I've got internal mesh, but I've got side bottom walls, and I've got my top wall, and I got my front and back still. And again, I haven't run the solver. I've just gone through and I've relabeled, renamed all the scripts, or all the boundaries. So I've now got to come into each of these folders and ask myself, is everything up to date like it needs to be? I could come in here and try to now run my Laplacian foam. It's going to give me an error because in my block mesh dictionary and in my mesh now I have boundaries that are called top wall, side bottom walls, and front and back. But if I take a look at the T file in my 0 folder, I've got boundaries that are labeled patch 1, patch 2, patch 3, patch 4. And that's just by virtue of what the tutorial was based on. That's what the ANSYS file created a mesh that had these boundaries. And so I just need to go in and update my T file. I think my temperature throughout was initially 300. I've got 4 patches here. I only have 3 different boundaries, so I'm just going to get rid of this first one. And instead of patch 2, this is going to be labeled top wall. This one had a fixed value of 500. And then I have my side bottom walls. The type here was also a fixed value. And these were a value of 300. And then this last one is called front and back. And I forgot to highlight this on the, when we took this block mesh file from the cavity tutorial, and I forgot to highlight those, the fact that for the Z direction this was just type empty. And we're just going to be consistent with that. And that just means I don't really care about my third dimension. Or in this case, my front and back is my third dimension, but I don't care about those surfaces. They're just going to be empty. So now I've got a T file that is consistent with the boundary values of the problem, and the labels of them are consistent with what I've done in my block mesh. So I'm good to go there. Just looking through some of the other files, I've got my polymesh folder now that contains all my information of the mesh, my transport properties. The default here was, it was different than, this is my thermal diffusivity, which according to our problem statement was 1e to the minus 4. I've got in my system folder my block mesh dictionary. I've already updated that one. My control dictionary, I think we need to change this from the default values in the tutorial. And if I recall, we went to 100 seconds here, and we can probably get away with 0.05 or even bigger. I definitely don't want to write every 0.1 seconds. I think we had 25 seconds or so. So I update that file, and now I should be able to come in here and make sure I'm in the root directory of that problem and run my solver. I've got my mesh created, and I'm running my solver, and it stops at 100 seconds, and it should be saving every 25 seconds, and that's what we have. This is basically the tutorial that was the most recent one that you went through. And so now I can come to pair view, and you'll notice I still only have solid color in here, but if I take this, I want the internal mesh actually. And if I reload the data, reload the files, I should have some additional parameters in here because I successfully ran my solver. I've got temperatures, I've got gradients of temperature that I can plot, and this looks good. It looks like we've got 500 on the top, we've got 300 on the sides and bottom, and this problem is good to go. And so that's, hopefully that gives you a little bit more insight into what to look for in each of the files. If you're going to create a very simple mesh, you got to have that block mesh file in there, and make sure you're naming your boundaries consistently between not just the block mesh, but all the everything in the 0 folder is going to need to call out something for each of those boundaries, and you just want to make sure that the labels are consistent and the values that you input are consistent with the problem that you're trying to solve. Okay, so that was just a brief tutorial. Hopefully provide you some insight into file structure, etc. The next set of tutorials, we will start to look at specific examples where we have additional terms in our partial differential equation that we're trying to account for. We'll start with the easiest one, which is just heat generation, and we'll learn how to accommodate that in our OpenFOAM files. So that concludes this tutorial. Thanks. We'll see you soon.